I am Meche Malshani, E19235. Now I present my individual research project titled Experimental Analysis of Heat Transfer in a Mini-Channel Heat Exchanger functioning as an evaporator using propane as the refrigerant. This project was supervised by Professor Primal Fernando and is part of the ME420 Mechanical Engineering course at the University of Peradeniya. I would like to start with a brief introduction to the background of this research. Between 1986 and 2003, Sweden experienced significant growth in heat pump usage, with over 332,000 heat pumps installed. However, this led to challenges such as system complexity, high cost, technical expertise requirements, safety concerns, and environmental impacts of certain refrigerants. To address these issues, an efficient heat pump with reduced refrigerant charge was needed. Professor Primal Fernando's research explored ways to minimize refrigerant charge in small capacity heat pumps without compromising the performance. In a previous group project, we calculated heat transfer coefficients using experimental data from just 2 datasets. My aim now is to expand on that work by analyzing all experimental data, comparing the results, and modifying the correlations for better accuracy. In this project, I considered each segment between two temperature measurements as a small heat exchanger. For each segment, I obtained the necessary values based on the properties of the fluids used in the evaporator. Using these fluid properties, I proceeded with the observations and calculations. This approach allows for the accurate determination of the local heat transfer coefficients for each segment. In this slide, I detail how I approached the calculations to find local heat transfer coefficients. I first needed accurate fluid properties including enthalpies, mass flow rates, operating temperatures and pressures, and saturated temperatures like that. For the temperature measurements, I only had inlet and outlet temperatures of propane. However, I also had outlet and inlet pressures as well as the differential pressure of propane for each experiment. To ensure accurate calculations, I also observed the glycol temperature measurements for these sections. Although it is possible to obtain these values using property tables, it is impractical when dealing with over 2000 datasets. To address this, I used a fluid property calculator which allowed to efficiently determine most of the required details, including temperatures. I will explain later. I then applied the heat balance equation to determine the mass flow rate of the refrigerant for each segment. The equation is Q dot equal m dot refrigerant rate times H2 minus H1. Here Q dot is the heat transfer rate and m dot refrigerant rate is the refrigerant mass flow rate. From this, I calculated the mass flow rate for each segment using available pressures and temperature data. I utilized specialized software to obtain required fluid properties. This allowed me to determine enthalpies at saturated points, thermal conductivities, pressures, and temperatures. From these observations, I collected approximately 2000 data points, which were critical for performing detailed calculations. This slide outlines the timeline of my project. Looking ahead, my future work plan includes refining the theoretical calculations and validating the modified correlation against experimental results. Additionally, I will identify ways to enhance efficiency further and explore potential applications of the findings. These are the references until now. To conclude, my project investigates the efficiency of a mini-channel heat exchanger operating as an evaporator with propane as the refrigerant. The data analysis and improved correlations aim to enhance the performance of heat pumps while addressing environmental concerns. Thank you for your attention.